Okay, this is a velocity of slip analysis problem, and we are using a linkage from the book, figure P624, and the following are the givens. We have a velocity VA2 shown here. It is 20 inches per second. Length 2, our crank, has a length of 2.5, and let's just say those are inches for the sake of argument. And O4A is equal to 4.1 inches. That's the length from O4 up to this point here, A. That's 4.1 inches. And then we have O2, O4. That is the length from O2 to O4 here. That is 3.9 inches. We have theta 2, or the angle of our crank. It's a little bit below the horizontal here, and therefore we're calling that angle negative, but just think of it as 11.5 degrees. Theta 4 is an angle of 56 degrees, and I'll show that in a little bit. We have a theta trans equal to negative 61 degrees, a theta slip of 29 degrees. Both of these will be shown soon as I go through. And we're going to use a graphical method to do this velocity analysis, or let's call it slip velocity analysis, which means we're going to be using a protractor and a ruler to do the analysis. And we're asked to find the omega 2, or the angular velocity of the crank, omega 3, the angular velocity of the block here in the middle, omega 4, the angular velocity of this entire kind of curved slot, VA4, V slip, and V trans. And so let's go ahead and get started. So the first thing we want to do is recognize an effective length 4. And that's not uncommon in these slip velocity problems. So from O4 up to A is our effective length 4. And as you see, the length of it is going to be a changing length depending on what the crank is doing. The distance there that we've just drawn as our effective length 4 is going to change, as will its orientation. And let's go ahead and set its orientation up. It is equal to theta 4, and theta 4 was provided for us. Again, that's about 56 degrees, which is given to us up above. Next, we're going to use some different colors to draw in some of our other items. First, the slip velocity, or the slip axis. The slip axis is in green here. It's always, always, always parallel to the slot. We have a curved slot, but at this point, the crank, point A, is right at that location, so we're drawing a line parallel to the slot there. And the angle for the slip axis, that's a part of position analysis, so we're not doing it here. We were given that value, and that value is equal to 29 degrees. The next item that we want to write in is our velocity VA4. Again, it's perpendicular to effective length 4. We do not know how long it is, so I'm just drawing it here in red, and I'm going to label it VA4, perpendicular to our effective length 4. Next, to get VA4, we need to add something to VA2, and what we add is VA42. And I'm drawing VA42. It's always, 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 always parallel to the slip axis. And so I'm trying to draw a parallel here. It's blue, it's parallel to the slip axis. And in terms of our velocity vector triangle, VA4 is equal to VA2 plus VA42, which means that where VA2 ends, VA42 starts, and then you get VA4. So the head of VA4 and the head of VA42 should be at the same point, according to according to vector addition. So since we are doing a graphical method and VA2 was given to us as 20 inches per second, we can use that to measure and since it's a known item, we could use that as a ratio to find the other velocities in terms of inches per second. So it's equal to about 25 millimeters here on my protractor. And so what we're saying here for this drawing, 25 millimeters is equal to 20 inches per second. So let's measure VA4. And that looks like, what's that, about 20, I would say 21 millimeters. And we also want to measure our VA4 too, to get that as good as we can. It's graphical, so it's not going to be perfect, but you know, we're using the millimeter side of the ruler. It makes it a little easier. And that looks like about 22 millimeters, I think. Look there, a little bit. Oh no, we're over there, 26, about 26 millimeters. And another thing that they want us to find is our V-trans. And it's important that we remember that V-trans is always perpendicular to the slip axis. So V-slip is parallel to the slip axis, but V-trans is perpendicular to it. And so now we have our V-trans drawn in, and we should measure its length also. So we use our ruler, come in there, and it's looking like 20. But 20, I think that's about 20. Okay, a little bit less, about 19 millimeters. Very close, but a little bit less than 20 millimeters. So first thing they want us to find is omega 2. It was not given, but VA2 was given. And VA2 is equal to omega 2 times L2. So we take our VA2, which is 20 inches per second, and we divide it by our L2, which is 2.5 inches. Then we can find that our omega 2 is 8 radians per second, and it is clockwise. Remember, it's kind of shown right here that it's clockwise. And so it's 8 radians per second clockwise. Or you can think of it as negative 8 radians per second. And we have our VA4. It's equal to 21 millimeters. So we put that under here and get our ratio set up. Again, VA2 is our known, and it is 25 millimeters. So VA4 is equal to 20 inches per second divided by 25 times 21, or 16.8 inches per second is our VA4. So we found VA4, we found omega 2, so we're moving right along. Now we're ready to determine our omega 4, because once we find VA4, we can simply divide by L4, which in this case is that changing amount, that effective length, right, of length 4, or effective length, or I should say the length of the effective length 4, and that's O4A. But again, that's part of position analysis, was given to us as 4.1 inches. So VA4, 21 millimeters, 16.8 inches per second divided by O4A, or 4.1, gives us 4.1 radians per second. And it's also clockwise, because if you note, we have VA4 moving in this direction. That's going to cause length 4 to rotate in a clockwise direction, which means omega 4 should be clockwise or negative. And we also have the slider, length 3, inside of length 4, and so they have to have the same angular velocity. Otherwise, the block would break out of the slot. Now for V-trans. V-trans was 19 millimeters long. VA2 is 25 millimeters long. It's our known. And so V-trans is going to be equal to 20 inches per second divided by 25 times 19, or 15.2 inches per second. So we have our V-trans. Last but not least, our V-slip. V-slip is the same as VA42. VA42 is 26 millimeters long, equal to VA2 over 25 millimeters, meaning that our VA42 is going to be equal to 20 inches per second divided by 25 times 26, or 20.8 inches per second. And now we have our V-slip. So we found all of the items they asked us to find. Thank you for watching.